So divided difference table. Okay, so here it's really just a way of checking derivatives. It's an estimate on derivatives, and so if I have a x1, x2, x3, x4, x5, something like that, then I'm going to go with the notation I think that you all have. So f at x2, f at x3. So here are your data, f at x4, f at x5. Now, if I wanted to estimate the derivative, somewhere between x1 and x2, what I could do is I could take f at x2 minus f at x1 over x2 minus x1. So, kind of nasty penmanship, but at least I'm talking. So, okay, so there's our first divided difference. This is our 0th divided difference. Here's our first divided difference. And we could do the same thing here with f at x3 minus f at x2 and x3 minus x2 and f at x4 minus f at x3 over x4 minus x3, and that's good enough. There we go. We just had 4 data points. Okay, now to get our next divided difference, or sort of an estimate on the second derivative, actually all we have to do is, if we call this f1, these are f0, then what I want to do is take the f1s from 1 and 2 and 2 and 3 and subtract those, right? So if this is, and actually I don't remember the notation the text that I gave you uses, but if I call this one, I'm going to call this F1 and then 1, 2. Okay, and this one F1 and 2, 3. And this one F1, but then 3, 4. Okay, so that's my notation for this, the F1 for that part. So if I want this F2 here, all I do is I take the difference here of F1, 2, 3 minus F1, 1, 2. So I just take these two that we made here and divide by x3 minus x1. Okay, so we're going over this whole interval, and then similarly here, to get this divided difference, we would use f1 F1, 3, 4 minus F1, 2, 3, and then over x4 minus x2. And it just keeps working that way. So for our next one, we would take the difference of these two, but divide by x4 minus x1. So we just keep broadening this out. So the 1, notice there's just one space in between each x value, you know, x1 to x2, x2 to x3, x3 to x4. Under f2, we just take the numbers in the previous column for our difference, but then we divide by x's that are spaced by 2 in f2, and then in f3 we just take this column to the left and find differences for the numerator, but then we would take 3 steps between our x's, so we would have x1 and x4, and if we had more data it would just keep going on like that. So that's what a divided difference table is. You know, sort of why does it work okay, I guess. Well, hopefully this makes sense, you know, for a derivative. Well, and then what's a second derivative, right? F double prime of x is just the derivative of f prime, so I'll write it this way, there's f prime of x dx, right? And so, you know, what we're doing here is we're just taking the difference of the derivatives, divided by the change in x from x1 all the way to x3. Okay, so it's really that same idea. We're getting what we would call a centered difference in numerical language. We're getting a centered difference for that derivative, but you see each time we're just taking the difference of the previous column, which was the previous derivative, and then dividing by a larger and larger value of x, because we're taking a broader and broader difference here. You know, so hopefully that helps to make a little more sense of this and where it's coming from, those derivatives. It's not a tough calculation. Now, often tables, instead of, you know, here I tried to make the table taper down like that, and I've got some examples with Desmos and Excel that taper down like that. But actually often you'll see them either where they just kind of go across the row and they look more like a triangle like that, okay, or just the opposite, they'll keep building out but build out like that. And there's good reasons for either of those. This row, we did linear interpolation, right? Piecewise linear interpolation. But if you want to do a full polynomial interpolation, which we're just not going to do in this class, you end up wanting that top row of coefficients, those divided differences, to make it. And so actually to just build them out like this, not only is it easier computationally, but you can see the numbers you want a little better, I guess. And same thing here if you built them like this. Let's see, so those are our divided differences, and again, based on derivatives. So what you should find, and we'll have you look at this sort of thing, is if I have, you know, f of x is, say, a linear function, so a1x plus a b, something like that, then if that's the actual function and you were to make a divided difference table, then what you should find is that here are your x's, here are your y's, or your f of x's. Right, there's that. Now you do your divided difference, and when you do f1, you should get a constant term. This should be the same thing all the way down. And actually, right, if we took a couple values here like x1 and x2, and so what would you have here, right? You'd have a1 x1 plus b, and you'd have a2 x2 plus b. So when you do this first divided difference, you will have a2 x2 minus, oops, why did I say a2? That should be a1, a1 minus a1 x1, like that, over x2 minus x1, which is just a1. Right, so you should get the slope here. And then when you do it again, well, when I do x3, right, we should get a1 as well. These should all be the same value. And then when I go to f2, right, I'll take a1 minus a1 over x3 minus x1, and I'll get 0. Okay, so for if I think I basically have data that are a straight line, what I should see is in this first divided difference column, I should see a constant, or basically a constant. And then in the next row, I should see 0. And that's actually a decent way to decide how you might fit data. And of course, for anything polynomial, it continues that way. So let's add a page. You know, if I have f of x is a2 x squared plus a1 x plus b, well then what I would expect to see, you know, here's x, here's f of x, here's my first divided difference, f1, and here's my second divided difference, f2, and then my third divided difference, f3. And so, you know, here I expect a constant, right? Because if I look at f prime of x, I get 2a2x plus a1. Whoops, quit that. Just go back out here. Oh, I guess I have to hit the x. a1, and then I'll have to write it down here, I guess. F double prime of x is equal to 2a2, a constant. And so this playing the part of the second derivative, I should expect a constant there, 0 there, and so forth. So wherever I feel like I'm seeing a constant here in this column and then a 0 in that column, that maybe gives me a reasonable clue as to what degree polynomial I might want to do. You know, if this is out at the 5th column, then I might guess a 4th degree polynomial. But when that 0 is in the 2nd column, I tend to guess a linear. Okay, so that's kind of how we're going to use the divided difference table. It has again many other uses because you are looking at numerical derivatives, but for us, we're going to really use it just to help us decide what degree, if any. I mean, we may be trying to fit an exponential, which is not a polynomial, so we wouldn't have that. But if we're wondering whether a polynomial would fit, then a divided difference table is a nice way to go, and we'll actually see that in your project where we use a divided difference table. Okay, I guess that's about it.